This is a separation vector, right? It's the separation between two particles. If you have two particles falling in, these are trajectories, not world lines. They're just falling in straight in towards the center of the plane. Here's one particle. It has the vector r going towards it. Second particle, the vector r. Presumably they're at the same distance from the source, so these r's are the same length. This is the vector psi. Okay, I didn't draw it with a vector line, whatever, it's just a separation between these two. And as these things are falling, the separation vector is getting smaller. Okay? The acceleration of this guy is down towards the center. Acceleration of this guy is down towards the center. Right? A2 minus A1 is simply a vector in this direction. So the vector A2 minus A1 is in the same direction as psi. Correct?
Yeah.
Now what we want to find out is how much this is changing. What's the acceleration of psi, basically psi double dot. Okay, as this falls down, this is going to accelerate. It's going to get smaller and smaller and smaller. How will we measure that? What we'll do is simply take this acceleration minus this acceleration, and that's exactly what we want, with a little bit of a modification, which we'll see in a second. How will we get this amount, A2 minus A1? Can somebody suggest something? How would you measure that? I'm hiding the answer. Now we can plot this amount of separation or world line deviation. We can plot it as a function of time, right? And we're going to get a curve. Psi is a function of time. And then we can compute the curvature of psi as a function of time, which is simply the connection curvature, simply the second derivative with respect to the parameter. Just like our second derivative is the connection curvature of r, this is the connection curvature of the psi. If we then divide it by itself, so we get some kind of a relative deviation. In other words, we want to see how much this is changing relative to its original size. What fraction, percentage is it changing? Is it accelerating? Okay, so that gives us some kind of a relative curvature. Now, I call it both relative and absolute because when you divide by psi, you're taking it relative to itself, but that gives you more of an absolute measure of what's happening. Okay, so you can look at it both as a relative and absolute, but it's giving you a more correct version of what's happening because you're dividing it by itself to get the percentage change. Now, it's the Riemann curvature because this, right, this is a relative acceleration already. Just this alone is a relative acceleration. It's telling you the relative motion of the two, as opposed to r double dot by itself, which is an individual acceleration. So that's a very important difference. This psi is a relative feature. It has to do with two different world lines, right? Its second derivative is a relative acceleration. It's not just an acceleration. And then when you take this divided by itself, it gives you a measure of the Riemann curvature rather than just the connection curvature. Okay? Now, we know the second derivative, if you take its derivative with respect to r, you take the acceleration and look at it at different points along the fall, and take the comparison between the two, right? You get a measure of the Riemann curve, the relative acceleration of the separation vector. So you have a unified equation here which tells you what is the tidal acceleration, what is the world line separation or world line deviation between particles infalling in the vacuum outside a spherically symmetric source. Okay, again, is this equation clear? If it's not, then it is? Okay. And this is both for radial and angular separation. This is an extremely important equation. Okay, this is the foundation of just about everything.